which will be on the Knuth Pratt algorithm, which is a string matching algorithm. So let's get on with the video. So here's the core issue that we need to solve. We need to match a string within a much larger string. So as you can see here, we have two strings A and B, and we need to check if there is any instance of B inside string A. Right, so the basic approach that we could think of is check every possible substring in A. As you can see, we start at the first index in A. Then notice that there's no match. Then we check every single size tree based substring in A, and then we notice that yeah, only the last one matches, and we return that value. So you see, right, this is kind of inefficient, as we need to run through every single index. Moreover, if you look at this example, this is a two separate match cases. So in the first case, you notice that the third letter, which is C, does not match with X here, and in this case all three of them match. But you notice that here, right, the first two C's match in both scenarios. So is there a way for us to reduce unnecessary comparisons by skipping through some of these unnecessary searches again and reduce time complexity? It's because, like, when we are here, we are searching through, we are starting from here and looking for CC, CC and CX here, and then when we move here, we're also looking for CC, CC and comparing these two. So is there a way for us to reduce these unnecessary comparisons? Yes, there is. So we can reduce the repeated character checks by using the KMP algorithm, which I'll refer to as the prefix suffix algorithm here. As the purpose of this algorithm is to construct a prefix suffix array called PS, where PSI will have the longest common prefix and suffix up till index I. So PSI will contain the longest length for which the prefix of that subarray until the ith point is equal to the suffix. So what I mean here is, let's look at this subarray, right? So we start from A, then end here, and if there's a prefix suffix could be like A here, and then something here, and then another common prefix suffix could be like AY here, then if YC here. So if both of them are equal, then that's a valid prefix suffix, and we need to return the maximum possible length possible within this subarray. If you want to see an example, so let's assume that there is a subarray from here to here. Then you notice that the longest prefix suffix is going to be of length 2, because the prefix here is CC and the suffix here is CC, right? It's also possible for there to be a prefix suffix of 1, because there's a C here, there's a C here, but the maximum possible is 2, as you can see in this example here. So let's just run through what the algorithm would output as the PS array. So initially we set PS 0 to be 0. We make it in this algorithm, we make it a case that a string cannot be a prefix suffix of itself, which means that the maximum possible prefix suffix at any point I, any index I, it will be I. So what this means is that I cannot say that AP is a prefix suffix of AP, right? Because that's kind of trivial. So we're only looking for the maximum length of possible. In this case, it will be I will be 1. So if A had matched this this character here, and the longest prefix suffix at this point would have been 1. But we realize that it's 0 as A does not match P. Moreover, there is no common prefix suffix until this point as well, as AP does not match PT and A does not match T. The same case for this point in the array, there are no common prefix suffixes that could be matched. But when we do reach the 4th index in the array, we notice that A matches A here, so that's the prefix suffix length, as it's not possible to form any prefix suffix that is the same, that is larger than of length 1, because AP is not equal to YA and APT is not equal to TYA, right? We go on to the last index, then we notice that we have p here, which matches the p here. So we know that the maximum possible prefix suffix length as this index is going to be 2, as ap equals to ap. So how can we perform this algorithm? So let's say we have the current string a, right, which has a1, a2, a3, a bunch of stuff in the middle, and then ak plus 1, and ak plus 2. So assume that we're currently in this last position, as the arrow is pointing to this point, and we need to find the maximum length of a common prefix suffix at this point. So the KMP algorithm is a linear algorithm, and by the time you would have reached here, you would have already known what the largest common prefix suffix at this point would have been, which is the longest common prefix suffix from the beginning until this point in the array, right? So let's assume that we have generated the prefix suffix and realize that the largest prefix suffix at this point is 2. What this means is that a1 equals to ak, and a2 equals to ak plus 1. That's why the length is 2, right? So now at the last index, we want to check if it's possible for the prefix suffix to be 3. So we check if a2, which was 2 was the size of the previous prefix suffix, equals to ak plus 2. So a2 here will be a3, and what are you doing? We're checking whether a3 is equal to ak plus 2. If it is, it means that a1 is equal to ak, a2 is equal to ak plus 1, and a3 is equal to ak plus 2, which means that the prefix suffix at this point from the beginning to the end of the array is going to be 2 plus 1, which is going to be equal to 3. But what if it's the case where it isn't? Note that we know that the prefix suffix at I cannot be of length 3, right? Because a3 and ak plus 2 do not match. But it can be something smaller than that. So how can the previous prefix suffix that we've already calculated so far help us determine what it could be? We need to find a quick way to find the next candidate for the largest prefix suffix length. So let's explore this as an example. So let's say we have this string here, right? AB, ABX, a bunch of stuff in the middle, and then AB, ABA, right? So currently the last index, and then the prefix with the value here is A, and you know that this does not match with X here. So so this is the alternate case where the things don't match. And we know from the prefix suffix array that the prefix suffix length until this point is 4, which makes sense because ABAB is equal to ABAB, right? So it's 4. So since A minus 1, which is A, is not equal to A4, which is X, we know that the prefix suffix at this point is going to be less than 5. How do we find a candidate? Let's look at PS4 minus 1, which is until from the beginning to up to this point. It will bring us to this subarray. This is the longest prefix suffix of length 2. Note that we already know this because we have already calculated the prefix suffix from this point as we reach towards the end. So we know that this is the longest prefix suffix of length 2, as AB on the left matches AB on the right? Which means that we know that there will be an AB at the very left of the array and an AB at the very right of the array up to index I minus 1. This is because, like, let's say until this point, right, we know that there is a prefix suffix of AB. So what we definitely know is that there's an AB on the very left and there is an AB on the very right also, right? So what this means is that a candidate could be to check A2, which will be this point, and check if it's equal to this one. And if it is, then we know that the prefix suffix at this point is going to be 2 plus 1, which is going to be 3. So we can see from this example, right? So initially we had a prefix suffix of 4, which was noted to be 2. So we know that there's going to be AB at the very left of the string. There's going to be also going to be AB definitely at the very right of the string until that point. So we just check AB2. So if it matches with our current pointer here, then we definitely know that ABA will be ABA here. So we can set the prefix suffix at this index to be 3, as ABA is equal to ABA. Otherwise, we repeat the process until we reach 0 or the loop breaks. The next iteration, so let's say if A did not match A here, right? Then we need to update it to PS2 minus 1, because it used to be 2, so PS2 minus 1 is going to be the prefix suffix of length 1, which is going to be 0, as nothing really matches from the left and the right. So and then we pretty much can go to the left of the array and check at 0. We'll go through an example of that case here. So here's a case where the prefix suffix at like before our point is 0, right? So okay, so this is a similar scenario as in the previous case, where we are at this point. We notice that these two, they do not match, but we know that the previous prefix suffix is of length 4 at this point, as ABCD equals ABCD, right? Since x does not equal to A, then what we do is we try to go to the next candidate for the prefix suffix length, which will bring us to PS 4 minus 1, which is going to be 3, right? And what do we have here is a subarray called ABCD. So what does this tell us? The prefix suffix of this subarray is 0, as A does not equal D, and we cannot form any valid prefix suffix which are the same, right? So what does this mean? So this means that we definitely know that we are going to have an A at the very left of the array and a D at the very right of the array here, right? So A and D, and we already know that those do not match for sure. So yeah, we know that the very left of the array does not match the very right of the array until this point. But it is possible that the element that we are looking at right now, which is I, could match the 0th index. And in this case, right, you see that we have A at the very beginning of the array, and we have an A at the very end, which is our current pointer, and then the A's are equal. So we know for sure the prefix suffix at this point is going to be 1, as prefix is A and the suffix is A. That's the longest common prefix suffix that we have found. So yeah, this is a visual example of how that works. So you can see here only the A's are highlighted, and that's a common prefix suffix. So essentially what we're doing in this case is we're just checking whether the first element matches the current element, and if it does, and the prefix suffix is 1, otherwise it's 0. So let's say if it was A and T, right, then we know that there is no common prefix suffix for this entire subarray, and we can set prefix suffix at this index I to be 0. So let's first code out the algorithm before going into this use case. So we have a string S, and the result I will contain the largest prefix suffix length until that point. So again, you can assume res to be the PS array that we have computed here. Then initially we set the I pointer to be 1, and since we know that the 0th element in the prefix suffix array will be 0, we start from the first index instead. And J will be the initial prefix suffix length, and we set it to 0, because this makes sense, right? Because a string cannot be a prefix suffix of its whole self, right? So we construct a while loop for the generation of the result prefix suffix array, and yeah, this while loop runs until I is outside the length of the string, and we have a check here to check whether it's below the length of the string, right? And we set the initial J to be the maximum prefix suffix length until the previous index, right? This is what we have explored this example, where we set the prefix suffix of that we set J to be result I minus 1, which was 4 in that case, remember? So yeah, so and then this is the simple case where let's say Sj is equal to S of I, which is the case where both of them match. Then we can increment the prefix suffix length. So remember it went from 4 to 5, right? So yeah, so we set the prefix suffix array at index I to be j plus 1, and we can progress the I pointer forwards. Otherwise, which is a case where the strings do not match, the characters do not match, then you have a while loop until a valid match has been found. So this is the key important step here, which is j is equal to res j minus 1, which is what we did here, right? We set j is equal to res j minus 1, which was res 4, res 3, which was 2 here, right? Yeah. So as we go on, so we continue this while loop until we either find a match for which sj is equal to si, or the case where we have reached the very left of the array, right? So this is a case where we reach the very left of the array and these things do not really match at all. Then this is the case where we have to set prefix suffix at the current index to be 0, right? Because there's no prefix suffix of any length to be found at that point. And then we set j to be 0, as that is the current longest prefix suffix, and then we increment I by 1. Otherwise, this is a case where we do find a match after going through the while loop and decrementing the j. So we update the prefix suffix subarray at index I and set it to be j plus 1, right? And then we increment the I pointer. This is the same case. This is exactly the same as what we did in the if condition, if both strings had matched initially. So it's pretty much the same kind of thing that we're doing. So the core thing that can be solved using the KMP array more efficiently is string matching. So let's say we have our example here, which is what we started with in this video, right? So we generate the KMP array for the string that we're looking for. So the string we're looking for within the larger string is ccx. So you want to find out as a ccx within string A. So we generate a KMP array, and you can see initially it will be 0, and cc there's a match, so we set it to be 1. So that's a prefix suffix of length c. There's a prefix here of 1, suffix here of 1, and then ccx will become 0 again, as you can notice that c does not match with x. So we initially start off with 2 pointers, I for string A and j for string B, right? We initially set both of them to 0. So in the first case, since j equal to 0 and ai is not equal to bj, as you can see, a0 is not equal to b0, we can just progress the I pointer, as this I is definitely not a starting point for a valid match. Because you can see here, right, we are at the first point, and then the first characters do not even match directly. There's no point so we know for sure this is not a valid starting point. So we just progress the I pointer forwards. Just to progress the I pointer forwards, we check y, c again, they're not the same, so we progress it forward. And now we finally get a match with a2 matching b0, right? I is 2 and b is 0. So now we can progress both I and j, and we check for the next valid character in the string. So you finally get a match again, so c and c match, right? So we can progress both I and j from here to here, from here to here. And now we are at a point where we realize that ai and bj do not match, right? Notice that we can set the j pointer backwards, but where do we set it back to? J now becomes KMP j minus 1. Notice that KMP j minus 1 is 1, right? Because j is 2, 2 minus 1 is 1, and KMP 1 is 1, right? So we go back to this point and we check whether CC has been matched. And if it does, we can just proceed on, and then we realize that there has been a complete match made here, CCX and CCX. Notice that through this method, we are kind of saving necessary check on the first C here, right? Notice that we do not check whether this C is equal to this C, as we already kind of know that through the KMP array. So we're kind of saving up on searching on repeatedly comparing characters again and again. So yeah, so let's go through a general example on how downshifting j in this step where we set j equals to KMP j minus 1 works, right? So let's say we have these two strings. So A is the bigger string that we're looking for, that we are looking into. So B is what we want to find, right? So A has a bunch of stuff at the start, and then ABX, ABX. We're currently at I, right? We're currently at this point. And B is a string which has ABX, ABR. So we're currently at this I and this J, and we notice that these two do not match, right? AI is not equal to BJ. And notice that we have a KMP array of 0, 0, 0, 1, 2, 1. This makes sense because let's say 0, there's no prefix suffix at the first element. AB, they don't match, so there's no prefix suffix. And then AX, they don't match, so there's no prefix suffix. Now you look here, A and B, they do match. And that's the biggest common, that's the longest common prefix suffix, so the KMP array would have a value of 1. And look at AB here, and then AB here. So at this point, the prefix suffix will be of length 2, right? So notice here that let's say we set KMP j minus 1 is equal to 2, right? So let's say, so j is 1, 0, 1, 2, 3, 4, 5, right? So let's say j minus 1 is going to be 4, and KMP of 4 is 2. So what this means is that at this point in the string, there is a prefix suffix of length 2, right? So what we know is that there is an AB on the left and there is an AB on the right, right? So what this means is that right before this point here, highlighted in green, we will definitely see an AB, because that is a suffix, right? That is a suffix of this common prefix suffix, and it's highlighted in green, right? So let's shift our j to KMP j minus 1, right? So we go to j becomes 2 here. So we notice that in this case this AB is a prefix, right? But this AB is a suffix. So what can we do here, right? So we now know that these two are definitely going to be the same as in this here is a prefix suffix, and there is a prefix here as a suffix here. So we can kind of save on needing to check these two strings again using the when we are trying to match the strings. So all we need to do is check whether AI, which is x, is equal to bj, which is x. And if it is, then what we know is that we can continue the search for a match from this position onwards. So we're kind of saving on these two searches which are kind of redundant, right? This is possible only because we knew that from the KMP array that there is a common prefix suffix of length 2. If they hadn't matched, like let's say if AI was not equal to bj, then we will repeat the procedure of finding prefix suffixes to reduce repeated searches. So j would now become KMP j minus 1, which was KMP 2 minus 1, which is KMP 1, which will be here, and we know that there is no match between A and B, which will be 0. So we go all the way to the beginning again of the string B, because j is set to 0, right? So continuing on in this example, in this case we have pushed back our j to this point, and notice that both of them match, so we save on this extra search of C and C, and we can proceed forward with moving both pointers forward. So now we move both pointers forward and notice that we are at x and x, and moreover, more importantly, we have reached the end of B, right? So what this means is that since there is a match at the end of B, we know that all of B has been found within A. So we have reached the end of our search, and now can return the I for here, wherein there is a match string. There's a match for B within A, like CCX is in CCX within A, right? So that's the answer that we're looking for. So overall, the time complexity of this operation is going to be O1, as we have the KMP array, and looking up for previous indexes is only going to take O1 time, right? And the KMP array was generated through in a linear fashion, right? Through O1 time. And moreover, space complexity wise is going to be ON as well, as we have an additional KMP array which is of length B. So yeah, so that's the end of today's question. Thanks for watching the video, and hope to see you again.